Welcome back, chemists. In this video, we'll be focusing on how to apply the new skills that we've learned with dissociation equations, drawing particle diagrams, and describing the dissolving process to a new way to express chemical reactions using something called a net ionic equation. After this video, you will be able to predict the solubility of compounds using something called a solubility table, and write the complete and net ionic equations for a given reaction. So recall in the last lesson, you were asked to make a prediction about what the particle diagram would look like for an insoluble compound. And you may have had the question, well, how do I know which substances will be insoluble in water? Well, in chemistry, there's these things called solubility rules that basically chemists will memorize so they know which substances are going to be insoluble. Now, for your purposes, more than likely your teacher will give you a table that you will just use in order to determine the solubility. You won't actually have to memorize these rules. So solubility tables look different from resource to resource, but this is a really simple one that I made for you. And so you want to become really familiar with this one because chances are this will be the one that your teacher is using in class. I think the best way to understand how to use the solubility table is just to jump right in and try some examples. So let's take a look at some examples. So you have to be able to tell the solubility of substances. So if I ask you to predict the solubility of the following compounds, let's start with KCl. So what we would do is we would consult our solubility table, and we want to pick the rule that applies. So take a moment and know that it's potassium chloride or KCl that we're looking for. See if you can figure out what the solubility is going to be. First, look for the rule and then decide on the solubility. Hopefully you settled on this one right here. So hopefully you can see that KCl includes the ion chloride. And so notice that chloride is on the left underneath where it says soluble compounds. So what this is telling us is that all chlorides will be soluble with the exception of the three listed on the right. So like let's say for example it wasn't potassium chloride, let's say it was silver chloride, or let's say it was mercury 1 chloride, or lead 2 chloride. Those would be insoluble. However, it's potassium chloride, so therefore that would be a soluble compound. So all we would do is write soluble. Let's look at magnesium carbonate. So again, decide on the rule that you're going to use to decide whether it's soluble or not. And hopefully you settled on this one. So carbonates are listed in the insoluble compounds category. Now notice the little note in the lower right-hand corner. It says compounds that contain these anions are soluble if they contain group 1 metals or ammonium cations. So this obviously is not a group 1 metal, and it is not an ammonium cation, so therefore we would consider this carbonate, magnesium carbonate, to be insoluble. So now we have iron 3 oxide. Again, look for the rule. Notice that this is also listed in the insoluble compound category. Iron is not a group 1 metal, and it's certainly not ammonium, so therefore this one is also considered to be insoluble. This is copper 2 nitrate. So you want to look again for one of the ions in the solubility table, and right away I see nitrates are listed as the soluble compound. And so it looks like nitrates are always going to be soluble, all the time. So therefore this is going to be a soluble compound. And then one more, we've got calcium fluoride. So these are the fluoride, that's the fluoride rule. And you can see that calcium is listed as an exception, meaning that calcium fluoride would be insoluble. So if calcium combines with the fluoride ion, that is going to be an insoluble compound. So like I said, this is something that you'll always have on any test or quiz. You won't actually have to memorize it. You'll just be using that solubility table. Okay, so now we have to talk about showing reactions in aqueous solutions. So to show reactions that involve ions, chemists will use something called ionic equations. Ionic equations differ from chemical equations in that the substances that are ions in solution are written as ions in the equation. So it's almost like you've got a bunch of like little dissociation equations in your large chemical reaction. Double replacement reactions are very commonly written in this manner. So a precipitation reaction is a type of double replacement reaction. They produce a water-insoluble product or a precipitate, and their reactions are usually water-soluble. If a cation and an anion are capable of coming together to form an insoluble substance, then a precipitate will form. Now, to determine if a precipitate will form, and this is why we practiced this earlier, we have to use the solubility table. So now what we're going to do is we're going to learn how to write net ionic equations. And I find that the easiest way to do this is to use a stepwise approach. So I'm going to describe the steps to you, and then we'll use the steps in the subsequent examples. So we're going to write the balanced formula equation. That's the first thing. We're going to use the solubility table to determine soluble and insoluble substances. Unless it's given to you in the actual prompt, you'll have to always do this. For any soluble substances, you're going to split the compound into its ions and separate each with a plus sign. The subscripts of the ions become coefficients, and you want to multiply the subscript and coefficient from the balanced equation, if need be. So again, this is kind of what I was talking about earlier. You're going to have almost little mini dissociation equations within your large chemical reaction. You will then have to cancel what we call spectator ions. So these are called spectators. If you think about spectators at a sporting event, these are the people that kind of stand around and just watch the game played. Now, spectator ions are kind of similar in that they're going to just stand around and watch the reaction happen. So these are ions that do not participate in the reaction, but they are there and they appear on either side of the equation, and all you'll do is cancel them out. And then finally, you're going to rewrite the equation, including the proper state of matter symbols and omitting those spectator ions. So let's try some examples. So I'm going to ask you to write the balanced net ionic equation for the reaction of aqueous barium chloride and sodium sulfate to give barium sulfate and sodium chloride. So notice in this example, you were actually given the reactants and the products. You were given the fact that the two substances that you're starting with are aqueous, but we're going to have to double check the solubilities of the barium sulfate and sodium chloride using our table. So balanced molecular equations first. You guys are really good at this. The double replacement reaction. You do want to make sure that it's balanced, and I did balance it for you. The first two substances in the prompt are listed as aqueous, so I'm going to throw the aqueous right in there. But now we want to check the barium sulfate using our solubility table. So if we look up barium sulfate, notice that sulfates are listed as soluble compounds. However, barium is an exception. So that means that this is absolutely going to be a solid in this case. And then you probably have prior knowledge that sodium chloride is soluble in water, but in case you want to check, you'll find the chloride ion is soluble, and it is not part of the exceptions, so therefore that is going to be aqueous. So that's your balanced molecular equation. Next up, you have to do the complete ionic equation. So what does this mean? Basically, you're going to take all of the aqueous substances and break them apart into their individual ions, taking careful note that you want to multiply by any subscripts and coefficients if needed. So for example, this is the entire complete ionic equation. Notice that the barium chloride is split up into Ba2+ and then 2 Cl minuses because there's 2 chloride ions for every 1 barium chloride formula unit. Same thing with sodium sulfate. There are 2 sodium ions for every 1 sulfate ion. Notice how barium sulfate, it is a solid, so that's why it's not dissociated in your complete ionic equation. And then finally, take note of sodium chloride in that there are 2 sodium and 2 chloride because there's a coefficient of 2 in front of that compound. So again, you're going to break up anything aqueous, and anything that's solid stays together. Then what you want to do is cross out the spectator ions. These are the ions that appear on either side of the equation. So we're going to go with the 2 sodium ions and then the 2 chloride ions. So that now your net ionic equation is whatever is remaining, and therefore it looks like that. Notice that when you do this, on either side of the equation, you're going to be balanced for both mass and charge, meaning like for every 1 barium on one side, you've got 1 barium on the other. For 1 sulfate, you've got 1 sulfate on the other side. So we're balanced for mass. And you also want to make sure you're balanced for charge, meaning like barium 2 plus on the left and sulfate 2 minus on the left adds up to an overall neutral charge. And then obviously barium sulfate on the right-hand side is also not charged. Let's try another one. So we're writing the balanced net ionic equation for the reaction of solid lead-2 hydroxide and hydrochloric acid. So the balanced molecular equation is going to be something that looks like that. I've already balanced it for you because you guys are really good at that by now. And then I do tell you that lead-2 hydroxide is a solid. And you can check, in fact, that hydroxides, for example, if you look, you can see hydroxides are insoluble compounds. And so we're definitely going to write that as solid. And then hydrochloric acid, again, chlorides are going to be considered soluble unless it's paired with one of those ions, so HCl is going to be aqueous. And then we have to check lead-2 chloride. So we're going to look at chlorides, and it looks like lead-2 chloride is in fact going to be a solid because you can see it's one of the exceptions. So that's going to be listed as a solid. And then water. Well, we don't need the solubility table here because we know that water is a liquid. So we're just going to write little liquid right there. Let's do the complete ionic equation. So remember, anything that's aqueous is going to break apart. Anything that's a solid and anything that's a liquid is going to stay together. It is not going to dissociate. So notice that the lead-2 hydroxide, the lead-2 chloride, and the water all stay intact. They are not dissociated. However, we can very clearly see that the 2 HCl that you have in the balanced molecular equation is now separated into those individual ions. Again, we have to cross out spectator ions, but guess what? There aren't any. So therefore, our net ionic equation is just going to be the same thing written all over again. I've got one more for you. So it says write the balanced net ionic equation for the reaction of sodium phosphate and potassium carbonate. So the balanced molecular equation will look something like this. Lots of coefficients in this one. And this one you want to be extra careful. So we're going to make sure that we look up each substance. So we've got sodium carbonate to start. So carbonates are typically insoluble, but again, notice in the lower right-hand corner it says compounds that contain these anions are soluble if they contain group 1 metals. Well, guess what? Sodium is a group 1 metal. It is in group 1 of the periodic table, so that is going to be aqueous. Potassium carbonate, again, a carbonate is technically insoluble. However, potassium is a group 1 metal as well. So therefore, that is also going to be aqueous. Sodium carbonate is next. Again, carbonates are typically insoluble, but sodium carbonate is we've got a group 1 metal in there, so that is also going to be aqueous. And then potassium phosphate. So if we look up phosphates, those are typically insoluble compounds. But again, potassium is a group 1 metal. So that is an exception, so that means that that is also going to be soluble. Now, if we were to do the complete ionic equation, we would have to break up every single one of these compounds. And you want to be really careful when you do this. So I'm going to give you a second and just look at my complete ionic equation. Notice that I have 6 sodium ions because I multiplied the 2, that's a coefficient, times the 3, that's the subscript. There are actually 6 ions of sodium. There are 2 ions of phosphate, 6 potassium ions, 3 carbonate ions. And so you can very clearly see when it comes time to cross out these spectator ions, look at this. Every single one cancels out. So what does this mean? Well, it means that there's no net ionic equation because there's no net reaction. There's no change. So this is a prime example of whenever you have everything that's a spectator ion, you can simply just write no reaction. So that'll make your life a lot easier. So here are some important points that I want to make. First of all, always check the solubility table to decide if a substance will be aqueous or a solid. Any substance other than a water-soluble substance will not break up into ions and therefore will be labeled with the symbols solid, liquid, or gas. For our purposes, if you see an acid listed, you can always assume that that's going to be aqueous. There are some solid acids, but don't worry about that for right now. Just in our class, we'll just assume that they're always going to be considered aqueous. And then no reaction will occur if two aqueous substances are produced. And then finally, a reaction will occur if a new solid, liquid, or a gas is produced. All right, chemists, this is a skill, so make sure you practice your skills. That's going to be so important to make sure that you're successful in the rest of this unit. Thank you so much for watching.